Welcome back to the Math Professors. Enjoy content that can be found in any college math class? Please consider liking, subscribing, and sharing. I'm Professor Van Hamlin, and I'm going to cover eigenvalues and eigenvectors. So previously we discussed the kernel of a transformation, and the kernel being the transformation of vector v being equal to the 0 vector. And we know that transformations can be written as matrix multiplication, so T of v can be defined by A times v, which is equal to the 0 vector, and that corresponds to the null space of matrix A. So we've talked about when this matrix multiplication is equal to 0, when the transformation spits out 0, but what about, say, the identity transformation? What that would mean is, what about when T of v is equal to itself? So when does the vector v map or transform directly to itself? So what I want to do is I want to consider this matrix A and this matrix in this vector v, and I'm going to do multiplication. So T of v being defined through matrix multiplication. So let's say T of vector v is going to be defined by A times v. So we're going to say this is going to be the matrix 4, 3, 1, 2, and I'm going to multiply by the matrix say 3, 1. Now with a little bit of matrix multiplication, row times column, we're going to get 15 here, and then very similar, 1 times 3 plus 2 times 1 is going to be equal to 5. So what we can see is that T of v, which is A times v, well, A times v is equal to 15, 5, which is not exactly 3, 1, but this is equal to 5 times the vector 3, 1. So we don't tend to ask, the exact identity transformation. We tend to ask, when can I take this matrix, multiply by a vector, and then I get a scalar of that original vector? So something a little less restrictive than just say 1 times v. What if I have some lambda times v? So that's really what we're talking about is we want to find, all vectors v such that if I take our matrix A times v, I get some scalar multiple of v. And this is what we're going to define to be the eigenvalue. So in this case, the eigenvalue is going to be equal to 5. And the eigenvector is going to be equal to that 3, 1. Okay, so now when we say the eigenvalue is equal to 5 and the eigenvector is equal to 3, 1, now this is the eigenvalue of matrix A and this is the eigenvector of matrix A. So this is matrix dependent. So this is, I would say, of matrix A, which is going to be equal to that 4, 3, 1, 2. So let's kind of discuss what eigenvectors and eigenvalues are, maybe like in a real-world situation. So say we're looking at our globe, and we can say all the normal vectors coming off of our sphere would point outwards from that. Now we know that our globe goes through a transformation. It rotates. So when we ask what are the eigenvectors of its rotation, we can see that we have something like this. Let's pull up this coffee cup here. So let's say I have a normal vector of this coffee cup, and when I rotate it, we can see that that eigenvector is, this is not an eigenvector because it changes directions. Notice that this is an eigenvector because the original vector 3, 1 gave us 15, 5, which is a scalar multiple of 3, 1, so it is actually in the exact same direction as it was before. So if I do have some kind of rotational transformation, the only eigenvectors of this would be the one pointing straight up and down, because if I spin this, we can see that that thing doesn't actually move at all. Well, actually, we get 1 times the original vector. And even down here, if I spin it, we can see that this vector down here is also unchanged. All right, so what I'm going to be giving you is I'm going to be giving you matrices, and from these matrices, we're going to be able to find eigenvalues and eigenvectors. And we'll start with that matrix right here, and I'll explain a method on how to find these things. How do we generate eigenvalues and eigenvectors of a matrix? Well, we're trying to solve this. We're trying to solve that A times X is equal to some lambda times X. Now I wrote these things as vector v before, so we just know that x is this going to be this general vector. And the solutions will be, a specific v. Okay, so I'm trying to solve these things. So what I want to do is, I don't know how to solve for this, but I have, done a lot of previous work solving for zeros. So I'm going to send this a times x to the other side. Now, I'd love to be able to factor x out of here, but let me show you why we cannot. If I try to pull out an x, I'd have lambda minus a times x. And lambda is a scalar, and that means that this subtraction here is undefined because this is a matrix, maybe a 2 by 2 matrix or maybe a 3 by 3 matrix. So if I have like some like scalar 5 minus 1, 4, 2, 8, I wouldn't be able to subtract these two things because this needs to be also a 2 by 2 matrix. So what we're going to do here is I'm going to rewrite this lambda x as lambda I times x minus a x. Now this is where I is going to have the same size as a. So now when we factor out our x, I'm going to have lambda I minus a times x is going to be equal to 0 over here. So essentially what I'm trying to do is I'm trying to find really the null space of of this new matrix, and this new matrix is going to be lambda I minus a, and we're going to call this the characteristic matrix. So call this the characteristic matrix. Now, for this to have essentially solutions, if I'm going to find the null space of this, really I want to figure out when the determinant of this thing is going to be equal to 0, so that I can make this matrix singular, and that's really kind of the start of this. So let me kind of explain what I mean by this. What we know is this will definitely have a instant solution. If x is equal to 0, then anything times 0 is going to be equal to 0. But I don't want a trivial solution. What I'm trying to find is I'm trying to find the non-trivial vectors that make this true. So this thing will have non-trivial solutions if this matrix here is singular, or what we can say is that the determinant of lambda I minus a is equal to 0. So that's basically what we're going to do. We're going to be able to find the determinant of this thing is equal to 0. That's going to tell us what lambdas we need to make this thing true. And once we know lambda to be true, I can plug it back into this equation, and then this will give me that specific matrix, and then I can solve it just like I did with finding the kernel or finding the null space. So we're going to start out with, finding the determinant of the characteristic equation, make sure that it's singular, so we're going to make sure that the determinant is equal to 0. So what I need to do is I need to solve for the determinant of lambda I minus a is equal to 0. Now A is a 2 by 2 matrix, so I has to share its same size, so we're going to have the determinant, so just write this in absolute value form, of lambda times I, which is 1, 0, 0, 1, and then minus a, which is our 4, 3, 1, 2, and this thing has to be equal to 0. Alright, so cleaning this thing up, we know that we're going to have lambdas across the diagonal here, so this is going to be lambda 0, 0, lambda minus our a, 4, 3, 1, 2 is equal to 0, and now we can subtract, so lambda minus 4 0 minus 3 is going to be negative 3, 0 minus 1 is going to be negative 1, and then lambda minus 2 is equal to 0. Now, once you do this a lot, you'll know that it's going to be lambda minus the diagonal of the original, and then the opposite diagonals are just going to change sign. So then when we solve this, we're going to have to multiply across and then subtract. So this is going to be lambda minus 4 times lambda minus 2 minus, we have minus 3 times minus 1 is equal to 0. So lambda squared minus 2 lambda minus 4 lambda is minus 6 lambda. And then negative 4 times negative 2 is plus 8. And this is going to be positive 3, but minus a positive 3. So minus 3 is equal to 0. So we're going to get the quadratic equation. And most of your examples in the book, these things will factor nicely. If they don't, you have the quadratic formula. So this is going to be lambda minus 1 times lambda minus 5 is equal to 0. So we get two different eigenvalues. Lambda is equal to 1, and we also get lambda is equal to 5. Now we already knew this one, so let's prove from this one I get 3, 1. So now we know our characteristic, our true characteristic matrix, which we know is going to be equal to lambda I minus a. So that's going to be the characteristic equation, and well, the characteristic matrix. The characteristic equation is going to be essentially solving this thing's null space. So let's plug in lambda. So this is going to be when this is 5. Basically, it's this matrix right here. Is what we have. Lambda I minus a. So if I plug in 5 into those things, you're going to have 5, 0, 0, 5 minus the original A matrix, which is 4, 3, 1, 2. So 5 minus 4 is going to be 1, 0 minus 3, 0 minus 1, 5 minus 2, and this is going to be that matrix. So really what I have to do is I have to find the null space of this matrix, because I have to solve when does lambda I minus a times x is equal to 0. I'm trying to solve that, which essentially is, this characteristic matrix is right here. So I'm really just trying to solve this, that we have 1 minus 3 negative 1, 3 multiplied by this matrix. Well, this has to be a 2 by 2. So let's say this is x1, x2 is going to be equal to the 0 vector, which is 0, 0. And we have a bunch of ways of solving this using identities or row reducing. So let's row reduce, because these things row reduce very nicely. So put this in a joint form or augmented form. And then when I row reduce echelon form, what's going to happen is you can see that bottom row will just completely zero out. So this is 1, negative 3, 0. This is 0, 0, 0. Now remember, this is a system of equations. What this says is x1 minus 3x2 is equal to 0. So x1 minus 3x2 is equal to 0. And then what I can do is I can solve this for x1 is equal to minus 3x2. And then we'll parameterize this by letting x2 equal, say, t. So then finally our solution, our x1, x2 is going to be equal to, well, x1 is minus 3x2, which is t. So this is minus 3t, and x2 is just t. So when we try to find the null space of this, we know that when I pull out that t, that this is really just a linear combination of a vector times a scalar. So this is going to be equal to minus 3, 1 times t. So this is the eigenvector, because this, remember, this defines a subspace in R2, and this is the basis of that subspace. So if I want to say the basis of that subspace, S is going to be equal to minus 3, comma 1, which is the eigenvector. So this is the eigenvalue. This is the eigenvector, which is just a rewrite of that vertical matrix. So again, what this means is that any vector that lives on this line is going to be an vector. So I can choose any one of these, like anything times t. So if t is equal to 1, you get itself, right? If t is equal to 2, you're going to give negative 6, 2. If you multiply negative 6, 2 times this matrix, what it's going to give you is it's going to give you 5 times that original. So negative 6 times 5 is going to be negative 30, and then 2 times 5 is going to be 10. So I'm going to write it here. This is messy. I'm going to find the other one. But for instance, I was claiming that any vector on this line, and I just picked t equals 2. You can pick t equals negative 2. T equals 50, negative 50. It doesn't really matter. Any t value, but this is just a different one. So let's say when it's 2, I'd get negative 6, 2. If I multiply this out, I guarantee that this is going to be 5 times the original vector. So this is going to be negative 30, 10. So remember that this defines a subspace, and this is just the basis of that subspace. So any vector on that line will also be considered, an eigenvector. This just happens to be, one of its simplest forms. So really there are an infinite amount of vectors in there because it's a subspace. Okay, and what I mean is this is still 5 times the original vector. Lambda times, x. All right, let's find the other one because we already knew this one. My claim is since this is a 2 by 2 matrix that you're actually going to get 2 of these. In another video, what happens, maybe what happens if we get like repeated roots as well, and some interesting stuff from there. So we have another one. We did this one. We have to do this one. So what about when lambda is equal to 1? So this is, let's say this is when lambda is equal to 5. What about when lambda is equal to 1? So and this, instead of this being 5s, this is going to be 1. So we're going to have 1, 0, 0, 1 minus 4, 3, 1, 2. So what we're going to get is we're going to get this characteristic matrix of minus 3, 3. 0 minus 1 is going to be minus 1. And this is going to be minus 1 as well. Okay. Now this should be that's a minus 3. Okay. So what I know is that this is going to row reduce nicely where you're going to get a row full of zeros. Remember that this is immediately non-singular, so this should always happen. That's what we forced it, right? Made sure that it was non-singular. Okay, so what we need to do is we need to solve exactly the same thing. We need to solve this equation. So we're going to have minus 3, minus 1, minus 1, multiplied by the vector, x1, x2, is going to be equal to the 0 vector. So we can row reduce nicely. I would actually just turn everything into 1. So I would flip this minus 1, minus 1, minus 3, minus 3. And then actually I should have let's augment it first. 0, 0. And then minus 1, minus 1, minus 3, both 0, 0. Just switching row 1 to row 2. Multiplying row 1 by negative 1. So 1, 1, 0, 0. Minus 3, 0. And then 3 row 1 plus row 2 is going to be 1, 1, 0, 0, 0, 0. Now you probably could have solved that right away. It's up to you and how fast you want to go from here to here. Okay. Or plug it in your calculator if you want to. Plug that in your calculator, ask it to row reduce, it'll spit out that matrix. Now remember, this is a infinite set of solutions. This says x1 plus x2 is equal to 0. That's what that line right there says. The next line says 0 is equal to 0. So then x1 is going to be equal to negative x2. Let x2 equal t. So then our eigenvector, or basically find the basis of all these eigenvectors, is going to be equal to, well, x1 is negative x2, but x2 is t, so this is negative t, and x2 is just straight up t. So then when I factor out t, I'm going to get the basis of the subspace, which is negative 1, 1. So we'd say S is going to be equal to this basis right here. So again, we get another line because this is a one-dimensional subspace. So remember that you can always check these to see if you did it correctly. So I kind of plugged in negative 6, 1, but a quick check for each one of these is, I would do a quick check, like what is 4, 1, 2, and then times, this eigenvector, minus 3, 1, and this does indeed give you minus 15, 5, which is 5 times the original vector. So boom, I know that I did that right. I can do the exact same thing here too. So if I want to check this, remember it's supposed to be, if I multiply this matrix times this vector, this eigenvector, when I get back, I better get back 5 times the original. Well, 4 times -1 is -4. Plus 3 is going to be, what do we got here? Yeah, so this is going to be -1. And then 1 times -1 is 1, then plus 2 is going to be 1. Now remember what we're supposed to get is this gave us 5 times the vector because that came from here. This one comes from that eigenvalue, so that's why this is 1. This is equal to 1 times the original eigenvector. So that one checks out as well. Okay, so we can do other video. I'll do another one. We'll do maybe a 3x3, and then also maybe one that has a repeated on top of it. And we'll save that for another video. So if you like the content, please subscribe.